one error, that at one point we had something like this when we integrated over theta over 2. So I took it equal to sine QR, so which is not correct. This must be equal to iota sine QR. So that's why I have a negative iota at the end. Okay. So coming back to our previous session, we had seen that scalar Green function of wave equation of this type this type was, so since these equations are equivalent to something like this, and we found the Green functions for this equation by solving this equation, and we found that, let's say if I take only one case, the result was delta t minus t prime minus r over c 4 pi r. And if you remember, one step before this, which was the Green function in Fourier domain, in temporal Fourier domain, it was something like this. Iota k naught r over 4 pi r, right? We took its temporal Fourier transform to see that it comes out with this. Now these are the general results when our fields are both spatial and time dependent. Now let's see today what happens in electrostatics and magnetostatics. I will discuss electrostatics. Magnetostatics comes out similarly. In electrostatics, the potentials and sources are time independent. There is no time dependence. So in that case, the Green function would be, and first let's write the solution and equation. So before this, our solution, for example, for phi, it came out to be integration over r. It was rho of r prime like this. Okay, and similarly, A was where this R is this. Now let's let's see what happens with electrostatics. So our wave equation reduces to the Laplace equation. Sorry, Poisson equation. And the green function for this thing would be static case since k0 is omega over c and omega is 0 and p prime is also 0, so the green function is simply 1 over 4 pi r, and the solution of Poisson equation is so Poisson equation solution would then be 1 over 4 pi epsilon r integration over r prime. Let me write it like this. I just multiply the green function with the source and wrote this equation. या इसको आप वो phi से भी डायरेक्ट लिख सकते हैं, since there is no time dependence, t minus rc वाली टर्म भी नहीं होगी, and we get this. So this 1 over 4 pi epsilon, 1 over 4 pi r is actually the solution of this equation. Which is essentially Coulomb's law, right? So Coulomb law, in effect, is an electrostatic green function. कोई confusion यहाँ पर? तो ये जो पॉइसन इक्वेशन है, अगर आप सोर्स को डेल्टा ले लें तो सॉल्यूशन इज द ग्रीन फंक्शन. तो वो इक्वेशन में जस्ट आप सोर्स की जगह पे डेल्टा पुट कर दें, व्हाटएवर इज द सॉल्यूशन इज जी. हाँ, जो सेंसली यहाँ पे डेल स्क्वायर माइनस 1 ओवर सी स्क्वायर पार्शियल स्क्वायर ओवर पार्शियल टी स्क्वायर, तो आप यहाँ पे सिर्फ डेल स्क्वायर. लेकिन जस्ट टू एम्फसाइज, ये जो ग्रीन फंक्शन है इस इलेक्ट्रोस्टैटिक प्रॉब्लम का, इट इज फॉर अ सोर्स which is located at r prime and is 0 everywhere else, point source, and this G is the field at any point r. And the boundary condition is that the field goes to 0 at infinity. There is no other boundary condition. So what happens if we have boundaries and we want to find green function? Or we want to find the solution of Poisson equation in the presence of boundaries. In the when there are no boundaries, like you have an arbitrary charge distribution, let's say a line charge or surface or sphere or something like this, then you can use this equation to find field element. There are no other boundaries. But what happens if we have boundaries? When we have boundaries, there are certain conditions that must be satisfied at those boundaries. And then finding the solution of Poisson equation is much more challenging. So one of the methods is that we write the general solution of Poisson equation and also write the solution of Laplace equation when rho is 0, because then the general solution is sum of this particular integral and the solution of Laplace equation, del square phi equal to 0. You implement boundary conditions and then find the unknown constants and you get the solution. You will probably learn about that method once we have worked out the solution of Poisson equation in different coordinate systems. Another method is expanding the green function in an orthogonal, using an orthogonal set of functions. एक वो तरीका है, एक सिंपल तरीका है जिसको आज हम डिस्कस करेंगे. It's called method of images. Which is very useful when we have conducting boundaries and there are charges present close to them. And the method actually works best only if the boundaries are canonical boundaries, like they are simple boundaries. When we have more complicated boundaries, then we might have to resort to a numerical technique to find the solution of Poisson equation. So the method of images, I will explain it using examples. So the method basically is that you have, let's say, certain boundaries of, let's say, conducting boundaries. So on a conductor, the potential is 0 on the surface of the conductor. So let's say if you have a charge here and you want to find the field here, so in this method, what we do, and we are interested in finding the field only in this region, not inside this region. Because if this is a conductor, the potential is 0 anyway. So if we are interested in finding potential in this region, one way is that we replace these boundaries and this region with an equivalent charges, let's call them Q prime. The Q is at its original position, so that these charges have to be replaced in such a manner that the resultant field, the total field due to all of these charges satisfy this condition. And then we can find the total field in this region. Not in this region, but in the region outside this boundary. So हमारे पास let's say कोई conducting object है, उसके पास कोई charge पड़ा है. इस method के तहत हम ये करते हैं कि इस conducting body को यहाँ से उठा देते हैं and try to find a charge or a set of charges कि उनको अगर हम यहाँ पर रखें और वो सारे charges इस region के अंदर ही होने चाहिए, so that the net field satisfies the given boundary condition. And then we can find the field in the external region. Yes, actually I am not proving it, but the solution is unique in a region if we specify the potential on the boundary. इस Q को तो हम नहीं छोड़े, ये Q इधर ही लेते हैं. यहाँ पे हम इक्विवेलेंट चार्जेस प्लेस कर रहे हैं. जी जी. हाँ जी, क्योंकि essentially this charge creates a charge distribution on the surface of this conductor. So that is equivalent in some situation, not always, but in some situation, that situation is equivalent to a few charges at some places. And then the net field can be computed again. Okay. For example, let's take a couple of examples and then this method will be clear. Let's say we have a conducting boundary and a charge is placed at a distance d from this plane boundary. And the boundary condition is this, that this is a grounded conductor, that is, the potential on it is 0. And our job is to find the potential here. So this situation is equivalent to, and I will leave it to you to prove it. मैं इससे ज़्यादा complicated का prove करूँगा. This situation is equivalent to this situation. Let's say this is origin. This is origin. यहाँ पे charge Q है. अगर ये distance d है, we can place another charge of negative sign at a distance t on the other side. And then you see the total potential of this charge and this charge on this surface is still 0. So this situation simulates this boundary condition, that phi should be 0 on this plane. Since potential due to a single charge is तो ये माइनस क्यू है, ये प्लस क्यू है, हर पॉइंट पे, हर पॉइंट इस प्लेन पे जो हर पॉइंट है उसका डिस्टेंस दोनों चार्जेस से सेम है. So plus q minus q will cancel each other and we will get a total potential and this boundary is 0. So the boundary condition is satisfied. Now the potential in this region is simply the sum of the potential due to two charges let's say this is vector d minus t and this is vector d. So the potential at an arbitrary point r is r minus d plus 1 over 4 pi epsilon naught minus q r plus d. So this is the potential everywhere in this region. And we can quickly check that if I substitute, let's say, z is equal to 0 in this formula, I will get phi 0. You can check. क्योंकि इस प्लेन पर z 0 होगा ना. And since this d vector is only along z, so once we put z is equal to 0, both expressions will be exactly equal. क्योंकि r वेक्टर है ना x, y, z, ये d वेक्टर है सम d z हैट. तो ये मैग्नीट्यूड क्या बन जाएगी, x स्क्वायर प्लस y स्क्वायर प्लस z माइनस d स्क्वायर x स्क्वायर. ये मैग्नीट्यूड क्या बनेगी, x स्क्वायर प्लस y स्क्वायर प्लस z प्लस d होल स्क्वायर एंड दैट स्क्वायर. और अगर हम z 0 पुट कर दें तो ये एक्सप्रेशन और ये एक्सप्रेशन दोनों सेम हो जाएंगे एंड दे विल कैंसिल ईच अदर. क्योंकि यहाँ पे z माइनस d का स्क्वायर आएगा, यहाँ पे z प्लस d का स्क्वायर. व्हेन z is 0, both terms are the same, so we get fraction 0. And potential anywhere in this region is now given by this. And you can even compute what's the force on this charge q if it is placed near a conducting boundary. क्या होगी फोर्स को? There are two ways to compute the force. ठीक है, आप ये है z इज इक्वल टू 0 प्लेन, ठीक है, इस तरफ ये कंडक्टर है। आप एक इस तरह करें कि इस बाउंड्री के ऊपर जो चार्ज डेंसिटी है वो कंप्यूट करें। वो कैसे कंप्यूट की जा सकती है? लेट मी डू दैट फ्रॉम Maxwell equations. We know that this boundary condition has to be satisfied. आप जो ये मैक्सवेल इक्वेशन है, इस मैक्सवेल इक्वेशन को लें एंड when you solve this equation, let's say there is a boundary here with surface charge density sigma. एक आप let's say pill box assume कर लें, ठीक है, यहाँ पर फील्ड E1 है, यहाँ पर फील्ड E2 है, and let's say that there is a unit normal N that points from 1 to 2, and then you take the वॉल्यूम इंटीग्रल ऑफ दिस इक्वेशन ऑन बोथ साइड, क्या बन जाएगा? ये आपने ड्राइव की हुई है इस क्लास कोर्स में कहीं पे? ओके, सो लेट्स ड्राइव इट. सो दिस बिकम्स लाइक दिस. सो इस पिल बॉक्स के ऊपर ये इंटीग्रल होगा. इफ आई स्क्वीज दिस पिल बॉक्स so that this interface and this interface lies just next to this boundary on this side and on this side, the integral on this curved surface will be 0 because it is approaching a 0 length. So ये surface 0 हो जाएगी. So ये जो integral है ये सिर्फ एक ही surface पे होगा, एक ही surface पे होगा. Let's say the surface area is A. So what we get is say field on this side is E1, and let's say the normal on this side is now minus N12, right? अगर ये normal N12 है तो ये normal minus N12 होगा. तो यहाँ पर इंटीग्रल क्या होगा? E1 डॉट N12, और यहाँ पर इंटीग्रल क्या होगा? E2 डॉट N12 into this surface area A. So ये A उधर ले जाए, Q over A is sigma, so there has to be an epsilon naught here. So we can compute surface charge density from this equation. With this normal goes from one side to the second side. दोस्तों समझ आ रही है आपको? So coming back to the problem, हमारे पास यहाँ पे चार्ज है Q. So one way to compute this charge Q is finding this sigma. अब जो है ये कंडक्टिंग बाउंड्री है, ये सारा कंडक्टर है इधर. इस साइड पे फील्ड क्या होगा? Let's say this is our normal, which is in this case simply z vector. So this is field E1 here, field E2 here. So the sigma on this is given by this, and since E1 is 0 because this is a conductor, so sigma on this conducting boundary is, this is simply z hat epsilon naught डॉट E2, एंड इसको आप पोटेंशियल की फॉर्म में लिख सकते हैं. कैसे? अगर मैं E2 की जगह पे माइनस डेल फाइव पुट कर दूं, सो दिस इज माइनस एप्सिलॉन नॉट z डॉट डेल फाइव माइनस एप्सिलॉन नॉट पार्शियल फाइव या पार्शियल z. सो दिस इज एट द बाउंड्री. Remember, all these equations are true only at the boundary. क्योंकि हमने स्क्रू बैग्स को स्क्वीज करके तो ये इक्वेशन आ सकती है. So what you do, you have that total potential phi. You put it here, derivate with respect to z, and find this charge density sigma induced on this planar surface because of this charge q. And then you want to find the force on this one. Let's say take a small surface element. उसकी वजह से इस पर force find करें df and then integrate over the whole surface to find this force. ये जब यहाँ पे connecting boundary है and we have a point charge here. अगर इस तरफ ये hollow भी है, doesn't matter because on this surface the field will be zero, and since there is no charge on this side, the field is zero everywhere. And so when we have a conducting sheet, the problem is exactly the same if we have a conductor, which is filling the whole space. Doesn't matter. Okay. So one way of finding the force is that you find the force on this charge because of a differential element, and then integrate this force over this plane, and you find the total force. लेकिन एक सिंपल तरीका भी है using the method of images, क्योंकि हमने देखा है कि for things on this side we can replace this planar conductor by simply a point charge at minus q. So it means the force on q can also be written simply like this. These are just two charges, so what's the force between them? अगर मैं सिर्फ मैग्नीट्यूड की बात करूं, minus q square 4 pi distance square, distance is 2d. This is the force. So first of all, when you have a point charge in front of a neutral conducting body, still there is a force on that charge particle. क्योंकि वो charge particle एक oppositely signed charge distribution create करेगा उस conductor के ऊपर, और because of the opposite charge distribution there is an attractive force on the charge. Physically क्या आप देख सकते हैं, it's called induction. ये अगर conductor है, so conductor by definition is a body in which there are free charges that can also move freely. So neutral mean negative positive charges are all equal. If I bring, let's say, a positive charge here, it will repel the positive charge in it away and negative charges towards the surface. So since positive charges are far away, and if it is grounded, it means it is connected to a reservoir of charges. So that positive charge essentially moves away into that reservoir. So what this conductor is left with is a negative charge on the surface. If it is an insulated body but conductor, so let's say it's above the ground, then this side will become negatively charged and its farther ends will become positively charged. But for the purpose of this negative charge, for example this table will attract this charge. क्योंकि इसके अंदर जो negative charges हैं वो surface पे आ गए and they are attracting this positive charge, and the force is given by this. And as the charge moves towards the conductor, you see the force rapidly increases. क्योंकि ये जो problem है, this is equivalent to this problem. So all of this side is equivalent to a point charge at a distance d on this side. So essentially, for the force on this charge is simply due to this point charge. आप इसको verify कर सकते हैं by this method as well. ये भी मैंने method आपको बताया. That what you do, you solve the original problem. That once you have potentials, first के लिए आपने potential image तरीके से find करनी है. This conducting sheet will have a charge distribution. अब वो charge distribution इससे find कर सकते हैं. And once you have a charge distribution, you can find the force due to a differential element and then integrate over the whole plane, and you can find the net force. It will also come out to be the same. Force is what? नहीं doesn't miss हो गया. Thank you. This usual Coulomb law. Units, if you specify them, they never create a problem. For example, आप length बता रहे हैं, आप मीटर में बता दें, मिलीमीटर में बता दें, that's fine. लेकिन अगर आप कुछ भी ना बताएं, then it's a trouble. And usually, except in let's say practical physics, advanced practical physics, people now use SI units. So when they don't say it, by default, it means SI units, which most electrodynamics books are using nowadays. Okay. So इस तरह से आप force find कर सकते हैं. Just a side point है. Let's say आपके पास कोई conductor है, which has lot of charges. आपको पता है work function क्या होता है किसी metal का? Well, and most of that energy is actually used in overcoming this force. क्यों? क्योंकि let's say it has a lot of free electrons in it. As soon as you take this electron out of here on this side, this conductor starts to attract this electron. And when you have to move it away from it to infinity, you have to work against this force. So most of the energy that is spent in work function is actually used in overcoming this electrostatic force. क्यों की वजह से? बिल्कुल. We are assuming that it's going to infinity, so the other charges are at infinity. When we have a sufficiently thick metal, essentially we can ignore them. E1 is not there because it's a conductor. So in a conductor, there is no electric field. Even if there is an electric field momentarily, it is quickly brought to zero by the movement of charges. Surface is the surface of the conductor. This is all in the conductor. और जैसे मैंने शुरू में बताया, it doesn't have to be like a conductor going to infinity. Even if it is a little bit thicker conductor, जो इस side पे charges हैं, they will have no influence on the field on this side because surface के साथ के आगे फिर conductor है, and in the conductor field is zero, so on the other side field is zero. If the conductor is grounded, ठीक है, अगर ये grounded है, grounded means it's connected to a body of zero potential. So let's say आप ये finite है. अगर ये grounded नहीं है तो यहाँ पे negative, तो यहाँ पे positive charge आ जाएगा. उस सूरत में यहाँ पे कुछ field होगा. ठीक है? For example, you have a conducting shell which is insulated, and you put a point charge here. So this point charge, let's say, is positive. It will attract negative charges on this surface, and the positive charges will go to this surface, and we will have a field here, which actually by Gauss law comes out to be exactly the same if this shell is not there. But if, let's say, this is connected to a ground, so these positive charges simply move to the ground, and then there is no field. But in this point, in this position, it is zero because it's a conductor. Okay. So when we have sufficiently thick conductor, we can actually assume that it's going to infinity for situation on this side. let's say it's not grounded. So this is the sheet and this is the charge. Okay? It's not grounded. Then this will create a charge distribution on this side. There is there's a charge, positive charge distribution, let's say on this side. First of all, this charge distribution will be different from this charge distribution because this is being influenced by this charge Q, and there's nothing to influence this charge distribution. This will be uniformly distributed. इस रीजन में फील्ड अभी भी जीरो है. So for the purpose of computing force on this charge Q, the problem is exactly still the same. That there's a zero field inside and there's a field on this side. So we compute sigma by this. यहाँ पे तो होगा फील्ड, लेकिन यहाँ पे फील्ड जीरो है इनसाइड द कंडक्टर. तो इस बाउंड्री को देखें, यहाँ पे फील्ड है, यहाँ पे फील्ड नहीं है. ठीक है. And in situations when there is field here, conceptually it's still straightforward. For example, आपके पास इलेक्ट्रिक बजाय डाइलेक्ट्रिक है, it's no big deal. और दोनों फील्ड रखें, you can still compute the charge density. ठीक है. Okay, so this was the simple situation, and in this case, what you can say that this potential is the green function of a point charge in front of a grounded planar conducting boundary when the charge is placed at distance. तो ये green function किसे कहते हैं? किसी point source के field, and this is for a point source field, but now this has boundary condition other than the condition at infinity. क्योंकि जब हम किसी मेटल से कोई चार्ज निकालते हैं, नेगेटिव हो पॉजिटिव हो डजंट मैटर. यहाँ से हमने देखा है कि whenever there is a charge in front of a conducting boundary, it experiences an attractive force. तो जो ही ये चार्ज बाहर आएगा, ये मेटल इसको दोबारा से अपने अंदर कैंसिल होगी. there is an attractive force. तो अगर आपने इस चार्ज को इंफिनिटी पे लेके जाना है, वर्क फंक्शन की डेफिनेशन है the amount of energy required to take the charge to infinity. When you have to take it to infinity, you have to work against this force. So आपने अब टोटल वर्क फंक्शन जो है वो किसके बराबर है? उसमें दो कंपोनेंट है. एक पार्ट एनर्जी का वो जो आपने स्पेंड किया था चार्ज को यहाँ से निकालकर यहाँ पर लाने के लिए. दूसरा पार्ट है which is usually the dominant part, is the part of energy that is spent to take this charge away from this boundary to infinity. Okay? And work function have both things included in it. दोनों ही जो भी फ्री चार्जेस हैं, they will move to that ground section. नहीं, because they are being attracted by this thing. Okay. So the ground is the zero potential thing. So if there are, let's say, free charges here, they will simply move there. या ग्राउंड को ये भी समझ सकते हैं, ग्राउंड इज लाइक एन इन्फिनिटली लॉन्ग कंडक्टर. ठीक है. तो ये जो चार्ज यहाँ पे है, it's attracting negative charges say on this side, so it's repelling positive charges to the other side, so the other side is at infinity, so those charges go to infinity. Okay, let's now solve another very important problem, which is point charge in front of a sphere. By the way, इसी मेथड को अगर आप ये प्लेनर वाले को एक्सटेंड करें, let's say you have a boundary like this. This is all conductor, and you place a charge Q here, and you want to compute fields in this region. You can replace this conductor with three other charges. Let's say this distance is x1, this distance is x2, you put a charge here, let's say minus q at x1. So this part is removed, and when you remove this part, you place a charge minus q2 at x and a charge at 2x2 of and then the field at any point in this region, not in this region. आप जो फार्मूला लिखेंगे मैथमेटिकली तो आपको यहाँ में भी कुछ ना कुछ दे देगा, but physically it's not correct. Now it's valid only in this region. So in this region the potential is sum of the potential due to these four charges. Anyway, so let's get to this problem. We have a grounded sphere, which means that the potential on its surface is 0 and its conducting sphere. Let me take this to be the coordinate system with origin at the center of the sphere. So let's say we have a point charge q at position vector y is equal to some yn prime and we want to find first of all the image charge, and then using that image charge we want to find the potential around the sphere, and then using that potential we also will calculate the surface charge density over the sphere and then the force between the sphere and the point charge. तो अब इस प्रॉब्लम को इन जनरल कॉम्प्लिकेट करके भी सॉल्व कर सकते हैं. You assume that the image charge is at an arbitrary position, let's say this point. You write the total potential due to this charge, and then substitute this r is equal to, let's say its radius is a. Substitute r is equal to a in the potential equation, and then solve for the coordinates and the magnitude of the image charge. लेकिन उतने complicate करने के बजाय I can use symmetry and argue that the image charge would be somewhere in front of this charge at, let's say, this position. And suppose its distance is y prime from the origin and its magnitude is q prime. So our job is to find q prime, y prime such that this boundary condition is satisfied. So let's take an arbitrary point. Let me call it R. Actually, I had called it X in my notes. So let me use X here. So this is Y. So at this point, what is the field? It's a field due to this charge and field due to this charge. So field due to this charge is simply Q over X minus Y, plus the field due to this is simply Q prime X minus Y, where Y is yn prime, y prime is y prime n prime, because they both are in the same direction, only the magnitude is different. And let's say X is some X n. So the unit vector in this direction is n. Okay? Now we have to find this unknown q prime and y prime from this single equation. So the मैंने कहा कि आप ये प्रॉब्लम शुरू कर सकते हैं टेकिंग बाय लेट्स से q prime anywhere arbitrarily anywhere inside and write the fleet, and then we see that the boundary condition is satisfied only if this is A. And I can argue that this charge should be on this by symmetry as well. अगर ये चार्ज यहाँ पर है तो इस स्फीयर के ऊपर चार्ज डिस्ट्रीब्यूशन किस तरह की होगी? सबसे ज़्यादा चार्ज यहाँ पे accumulate होगा इस सामने वाले सरफेस में। फिर जो आप स्फीयर इस पॉइंट से दूर जाएंगे तो चार्ज डेंसिटी कम होती जाएगी। So it means the equivalent charge must be on this axis. क्योंकि इस एक्सेस के अराउंड there is symmetry. So I took the image charge to be on the line joining origin and Q. So the boundary condition is this, that at x is equal to A, the potential must be 0. This is the boundary condition. At the surface of the sphere, potential is 0. So let's substitute x is equal to A. So we get 4 pi epsilon naught. Let's keep it. So we have Q AN minus YN prime plus Q prime AN minus Y prime N prime. So let's say we take A common from here. In this case, let me take Y prime common here. This is A over Y prime. अब अगर इस इक्वेशन को हम देखें तो this equation gives us 0 if Q over A is equal to P prime over Y prime and Y over A is equal to A over Y prime. क्योंकि जब ये इसके बराबर है, ये मैग्नीट्यूड दोनों बराबर हो जाएंगी. When this is equal to the negative of this, then this cancels with this thing. And we get 0. So let's solve this equation. This equation gives us y prime is equal to a square over y, and if we substitute this y prime here and solve for q prime, q prime is minus qa over y. So it means that this situation is equivalent to this situation. When you have a charge at a distance y away in front of a conducting grounded sphere, the sphere can be replaced by an image charge q prime at a distance y prime, where q prime y prime is 1 by 8. ये second line. So it's a mod, so it doesn't matter. ठीक है? So externally, this problem is equivalent to this. So now let's say we want to write solution at this point x. So the potential is 1 over 4 pi epsilon naught q x minus y, and q prime is minus qa over y x minus y. So this is the potential anywhere outside the sphere. ये फार्मूला आपको इनसाइड द स्फीयर भी वैल्यू देगा, बट दैट्स रॉन्ग, क्योंकि ये सिर्फ एप्लीकेबल है आउटसाइड द स्फीयर. इनसाइड द स्फीयर फील्ड इज जीरो. सिंस इट्स अ कंडक्टर, वी नो दैट. Let's try to expand it and find the result, final result. Q हम कॉमन ले लेते हैं. So this is x n hat minus y n hat prime minus a over y x n hat y n hat n prime So let's take x common here. And q prime की वैल्यू सही लिखी है. Okay, so let's substitute for y prime. और यहाँ से बल्कि y prime कॉमन ले लेते हैं जैसे पहले लिए. So this becomes n hat prime minus x over y prime. So y prime की वैल्यू जो है वो हम यहाँ से पुट कर देते हैं. So we get phi x q 4 pi epsilon naught. ये मैग्नीट्यूड हम ले सकते हैं, ठीक है, यूजिंग कोसाइन लॉ. ये बल्कि कोसाइन लॉ की भी जरूरत नहीं है. We can just multiply by term. So y prime is a square over y, so y cancels, 1a cancels, and we are left with 1 over a, 1 plus x square, and यहाँ भी y prime रख देते हैं a square over y, so y comes here, this is a square. So a square over y यहाँ पे आ गया. So this is x square y square over a4 minus 2 xy over a square. ये ठीक है. ये मैंने इस तरह से निकाला कि a वेक्टर प्लस b वेक्टर मैग्नीट्यूड जो है दिस इज इक्वल टू a प्लस b डॉट a प्लस b अंडर द स्क्वायर. n डॉट n 1 हो जाएगा, n हैट प्राइम डॉट n हैट प्राइम 1 हो जाएगा. तो जहां पे क्रॉस टर्म आ रही हो मैंने लिखी. सो दिस इज n हैट n वेक्टर and this is the unit vector in this direction. Let's say the angle between the two is gamma. So n hat prime is cosine gamma, and you substitute everything, the result comes out like this. Cosine gamma square root minus a for x square y square minus 2xy a square cosine gamma half. So this is the potential due to a point charge outside a grounded conducting sphere. On the other hand, this is also the green function for a grounded sphere. अगर आपको ये प्रॉब्लम सॉल्व करने को कहा जाए that you have a grounded conducting sphere and suppose there is a charged line in front of it, how will you solve the problem? You have the green function for one point charge on this line, and all you have to do is write charge distribution for this thing, and the total field is integrate over the line rho of r into this potential, let's call it G. So ये जो हम expression निकाल रहे हैं for point charges, they are useful in their own rights, but also in evaluating other charge distribution in similar situation. So by the way, आप यहाँ पर चार्ज डिस्ट्रीब्यूशन सिग्मा जो है स्फीयर की सरफेस पे वो भी कंप्यूट कर सकते हैं. कैसे? सिग्मा विल बी इन दिस केस माइनस एप्सिलॉन नॉट n hat dot del phi, which in this case is partial phi by partial n, क्योंकि एक्चुअली हमारा n के नाम है वेरिएबल x, so this is just partial phi by partial x. ये x जो लिखा हुआ है is what you usually call r, small r in spherical coordinates. ठीक है? अगर मैंने r लिया होता तो फिर ये partial phi by partial r होता. आप इसका डेरिवेटिव लें और x is equal to a पुट कर दें, you will have an expression for sigma. Let me just write the result. मैं आपको नोट्स भेज दूँगा, आप उनपे डेरिवेशन देख लीजिए. 3 and 4. Sigma comes out to be minus q 4 pi a square a over y 1 minus a square over y square 1 plus cosine. See, it actually only depends on gamma, and as it should. Gamma is the angle of the line joining the charge and origin and your observation point. So अगर हम assume करें कि जो charge है it is located twice the radius, तो charge distribution कुछ इस तरह से होगी. If we assume that it is 4 times the radius, then charge distribution is like this, where this is gamma 0 to 5. So I don't know how easy it is for you to imagine. Like you have this sphere, and let's say this is the point. इस पॉइंट और स्फीयर का जो ऑरिजिन है उसको जो लाइन मिला रही है the y line. जो गामा है वो कोई भी आप एक पॉइंट ले लें, इस पॉइंट ये जो लाइन है इसको जो इनके दरमियान में जो एंगल है वो गामा है. सो गामा 0 इज अ पॉइंट राइट इन फ्रंट ऑफ द चार्ज ऑन द स्फीयर. सो दिस इज द पॉइंट राइट इन फ्रंट ऑफ द चार्ज ऑन द स्फीयर. सो वहां पे चार्ज डेंसिटी मैक्सिमम है. एंड एज यू मूव अवे फ्रॉम दैट पॉइंट ऑन द स्फीयर, आप किसी भी डायरेक्शन में जाएं, अगर गामा कांस्टेंट है तो सेम वैल्यू है. सो जो चार्ज डेंसिटी है वो कम होती जा रही है. अगर मैं ये स्फीयर की टॉप सरफेस को देखूं, लेट्स से दिस इज अ पॉइंट जिसके सामने स्फीयर है, तो यहाँ पे चार्ज डेंसिटी मैक्सिमम है. फिर लेट्स से गामा 10 डिग्री अब जाते हैं, तो इन सब पॉइंट पे 10 डिग्री है, तो इन सब पॉइंट पे सिग्मा की वैल्यू सेम है क्योंकि सब पे गामा सेम. एंड देन यू मूव फर्दर अवे, द देन चार्ज डेंसिटी स्टार्ट्स टू डिक्रीज. और जो पॉइंट बिल्कुल ऑन द अदर साइड है, दैट इज गामा इज इक्वल टू पाई, एंड द चार्ज डेंसिटी इज स्टिल नॉट जीरो. There is some charge at that point as well. And in a case when sphere has a very small radius, I will देखिए when a is much smaller than y, so what happens that this term is neglected, this term is neglected, and we can actually take this thing. So इसको neglect कर दें, this is second order term. ये भी neglect हो जाएगी, ये बन गया 1 minus 2a over y कोसाइन गामा. ये ऊपर जाके minus half हो जाएगी, उसको expand करें तो आ जाएगा 1 plus half 2 से cancel हो जाएगा a over y कोसाइन गामा. फिर next term, फिर a over y इससे multiply होगी तो a over y आ जाएगा, इससे होगी तो a square हो जाएगा, उसको भी neglect कर दें. So what you are left with is 2 pi a square a over y. So this is the charge density induced on the sphere when the charge is placed far away from the sphere. And let's see what's the force between the charge sphere and the point charge. अब उसका वही तरीका है, एक तो एक आप सिग्मा यूज करें और इंटीग्रेशन से टोटल फोर्स कंप्यूट करें, ठीक है, क्योंकि पॉइंट चार्ज पर फोर्स भी होती है ना, QE, and what's the force on the point charge due to distribution of electric field? It would be, so dF is, let's say, dE, so then you integrate this dE, where dA has to be computed from sigma. उसकी बजाय चूंकि ये स्फीयर जो है वो पॉइंट चार्ज के इक्विवेलेंट है, I can directly write the force, the magnitude of the force by Coulomb law, 1 over 4 pi epsilon naught. One charge is Q, the other charge is Q prime, and what's the distance between the two? The distance is y minus y prime. Right? Y coordinate है इसका, y prime इसका, तो जो total distance है between the two is the difference. और अगर आप ये substitute करें, you get this thing. And let me show a couple of plots for this. Let's say this is y over a. This is origin. So this is 1. So 1 is the point when y is equal to a. So the charge cannot be inside the sphere, charge is outside. So the force is something like this. So the force goes to 0 as y goes to infinity, and force is infinite at y is equal to a, where the charge is just touching the sphere, the surface of the sphere. but everywhere the force remains negative. क्यों? क्योंकि I think I missed a negative sign. So Q prime is minus Q over whatever. So the force is negative everywhere. It means the force is attractive between a point charge and a grounded sphere. ये जो अगेन अच्छा हमने ये बात कर ली, यहाँ तक कोई कंफ्यूजन या कोई कंसर्न? कौन सा वाला? This is the surface charge density on the sphere as a function of gamma. So gamma is the angle between the line joining the charge and origin and your point on the surface of the sphere. So gamma 0 is this point, and as gamma increases, we go from here to here. At maximum, gamma can be pi, which is the point on the opposite side of the sphere. Okay?
So where does this method go? Situation change.
So unfortunately we didn't do that, but I think we will probably do it. That when we have the solution of Poisson equation and let's say Laplace equation, we will see that in potential theory, the unique solution at any point is specified by a given boundary condition. So if you satisfy a certain condition on a boundary, the solution is unique. There's only one solution. And since in this method, the method simulates exactly the same boundary condition on the surface of the sphere as the original problem, the solution, since solution is unique, for the same boundary condition, the solution of this problem and the original problem is the same. Okay. So we'll, I think in continuation of green function, Bobersov will probably at certain point will formally solve this problem that if we have boundary conditions on a given surface, and let's solve the equation and find potential at certain point, the solution only depends on the charge density and the boundary condition. Any other question? Okay. Now the next point is the continuation of this thing, and that is, let's say the sphere is conducting, but it's not grounded, and it is also charged. There is charge Q on it, and it is not grounded, and we have a point charge Q in front of it. What is the field outside the sphere? So we can solve this problem using the previous result in this manner. Let's say we came to this situation via this route. That initially there was no charge in it, and let's say it was grounded. So when it was grounded, and we place a charge Q here, we know that an image charge Q prime is set up here. So let's say now we disconnect from ground. So what's the total amount of charge on this sphere? Q prime. How much charge we should add to it to make the total charge Q? We should add Q minus Q prime to it so that the total charge is Q. Now this charge which is being added to this sphere will be uniformly distributed on the surface of the sphere, since it is unaffected by this charge Q, because its effect is already countered by this image charge Q prime at the boundary. So the net field at any point is the sum of three potentials Now this additional charge, since it is being uniformly distributed on the points outside the sphere of a uniform charge distribution, this charge acts as if this charge is located right at the center. So the contribution to field because of this charge is simply this.
So you can't distribute very
Uniformly over the surface of the sphere. So essentially, जो Q charge वाला sphere है in front of charge Q, it's equivalent to a charge Q minus Q prime distributed uniformly plus an image charge Q prime at a position given by those coordinates y prime and this thing. ये जो coordinate. Okay, so we are running out of time. So you can substitute everything. This is just x, since the uniformly distributed charge over the surface of a sphere is equivalent to a point charge at the center of the sphere for all points outside the sphere. So आप इसको solve करें, which I have already done here. And you can find the total potential. It's a complicated formula, doesn't tell much about the potential. And similarly, when you have to compute the force Q on this charge, what would be that force? It would be the force exerted by this charge. Y minus Y bar plus there is an additional force exerted by this charge Q minus Q prime at the center of the sphere, which is Q minus Q prime 4 pi epsilon naught Y square. क्योंकि टोटल तीन चार्ज है ना, एक यहाँ पे Q प्राइम सेंटर पे ये है, तो इसका और इसका डिस्टेंस सिंपली y है, क्योंकि इसका ओरिजिन से डिस्टेंस y था, इनके दरमियान में डिस्टेंस y माइनस y प्राइम है, सो वी गेट दिस. अब अगर इस फोर्स की हम उसी तरह की डायग्राम बनाए जो पहले बनाई थी, लेट्स से y ओवर a origin, this is 1. Now if Q is 0, we get the same situation as before. And the force on the particle is like this. If Q is not negative, the additional charge, Q minus Q prime is negative, so the force will be attractive, again like this. But if Q is positive, let's say this Q is positive, and the added charge is also positive, and it's if it is positive, the force is then like this. For a certain range, the force is repulsive. और जो कि होना भी चाहिए, अगर आपके पास एक यहाँ पे चार्ज स्फीयर है, पॉजिटिव चार्ज स्फीयर, ये पॉइंट चार्ज है पॉजिटिव, और दोनों बहुत दूर दूर हैं, तो essentially इसकी वजह से जो Q प्राइम है, it's significantly small because when y is large, अब देखें Q prime is inversely proportional to y, so Q prime is invisible. Then the force between the two is this positive charge and this Q repulsive force. But when it comes closer, ये जो Q है, ये इसके अंदर इमेज चार्ज क्रिएट कर रहा है, जिसकी स्ट्रेंथ बढ़ती जा रही है with smaller distance. And at certain point, the negative charge accumulated at the image position is stronger than the already placed positive charge in the sphere, and then the force becomes attractive. So ये initially counterintuitive हो सकता है कि आप एक positively charged sphere है, उसके पास एक positive charge लेके आते हैं, लेकिन अगर वो जो charge आप लेके आ रहे हैं, it's placed close enough, instead of a repulsive force, there is actually an attractive force. Because it's a conductor, and this positive charge is inducing a negative image charge, which is attracting it. What do you mean by attractive? I mean, we can verify this thing experimentally if we want to. ये नोट्स मैं आप लोगों को भेज दूंगा, इस पे कंपटीशन सारी हुई है, आप इनमें से बहुत हो हैं। इसके अलावा मैं कोशिश करूंगा कि इस लेक्चर से रिलेटेड आपको कुछ प्रॉब्लम्स भी भेज दूँ, जो बेसिकली जैक्सन की बुक्स हैं, लिटिल बिट डिफिकल्ट, तो आप उनको करने की कोशिश करें, ना हो तो आप मुझसे डिस्कशन कर सकते हो। इन द नेक्स्ट वीक दे विल प्रॉब्ली बी अ क्विज एज वेल, बाबर साहब कह रहे थे, तो बी रेडी फॉर दैट। और होमवर्क 2 जो है वो भी इस हफ्ते में चला जाएगा। जी वो कह रहे थे कि आज भेज देंगे, तो मे बी एट मोस्ट बाय टुमारो। एंड in the week after the following week, we'll probably have our first meeting. Okay, thank you.